There were 4 of them, according to the ancient Greeks. They named them Boreas, which came from the north, Eurus from the east, Notus from the south, and Zephyrus from the west. But today, those names have been forgotten, replaced by many others all over the world. One name is Fame, another Mistral, others Williwaw, Chinook, Norval. But they all stand for wind. Surface wind, wind aloft, headwind, tailwind, crosswind, and so forth. Wind is not a simple element of flight. It has many effects on weather and on aviation. It is a form of energy and action that has its origin in the radiant energy of the sun. The sun's rays cause some parts of the Earth to become warmer than others because of differences in heat absorption rates, cloud shading, and so forth. Let's consider air circulation on a global scale and ignore for the moment the Earth's rotation. The equatorial regions receive the greatest heating from the sun. The air in these regions rises, reaching a very high altitude. The air flows toward the poles, down the thermal gradient, that is, from high temperatures to low temperatures. The air descends or subsides at the poles, tending to flow along the surface back toward the equator. The rising air, or convection, at the equator, with converging air filling in, results in the equatorial low, a semi-permanent band of low pressure. The subsidence at the poles results in high pressure, with diverging airflow away from the polar regions. This semi-permanent system is termed the polar high. Some of the rising air does not reach the poles, however, and subsides near the 30-degree latitude. This subsidence results in a band of higher pressure, with divergence at the surface both toward the equator and northward. The Pacific High and the Bermuda High are 2 of these regions. The northward flowing air and the southerly airflow from the polar regions converge near the 60-degree latitude. This convergence results in convection and another semi-permanent region of low pressure. The Aleutian Low and the Icelandic Low are 2 of these regions. These areas of convection and subsidence, with high and low pressure areas, provide the global circulation of our atmosphere. But our Earth is not stationary, and the north and south movement of air is acted on by other forces. On a local scale, during daytime, the sun heats the landmass. But the sea's relatively stable temperature does not rise as readily. Consequently, there are ascending convective currents of air over the land, while the air over the water subsides or falls toward the surface. The air over the land converges. That over the sea diverges. The area over the water has relatively higher pressure than the area over the land. This air moves to fill the space left by the rising air. Maximum onshore wind occurs in mid-afternoon, when the land areas are the warmest. This is the sea breeze theory. At night, the land cools faster than the sea, and the flow is reversed. This offshore wind is called a land breeze. A plowed field heats up faster than an area covered by trees or vegetation. The air above the warmer area expands and rises, leaving a region of lower pressure. The nearby air, being under relatively higher pressure, tends to flow into the lower pressure areas. It is the difference in pressures that creates the force that moves the air from a more dense region to a less dense region. We call it pressure gradient force. Let's take a closer look at this force. When you use a pressure-actuated altimeter to fly a constant altitude, you maintain a constant pressure level. Your true height above sea level, however, varies throughout the air mass. This variation is usually not more than 15 to 100 feet or so in 100 miles of horizontal distance. If we select a large number of points with the same pressure altimeter reading, say 500 millibars, they would describe a surface of constant pressure. The 500 millibar surface height is approximately 18,000 feet. It completely surrounds the globe. You can draw any number of constant pressure surfaces. It's important to understand these surfaces because much weather information is displayed in terms of a given pressure altitude. Just as a surveyor describes a hill with lines that join all points that are at the same height above sea level, so meteorologists use contour lines to depict constant pressure surfaces and their height above sea level. The 500 millibar chart contours normally represent height differences of 200 feet and true altitude, that is, above sea level. They indicate the physical shape of the constant pressure surface. These lines are your key to the pressure gradient force, which always acts at right angles to the contours. Here is your first clue to wind flow. When the contours are widely spaced, you can expect the wind to be light. When they are tightly packed, they represent a large pressure gradient force and strong winds. A system with contour height values increasing toward the center is known as a high. It has a characteristic tendency to move the air outward from the center. When the center of a system is of lower contour value than the surrounding air, we have a low. The higher pressure establishes a pressure gradient force pointing in toward the center. Again, always directly across the contours. At first glance, it appears that the pressure gradient force would create wind that flows directly from a high to a low. It would, provided the Earth did not rotate. But it does turn, and that action makes airflows change direction. The force that does it is the same force that causes draining water to form a miniature whirlpool, counterclockwise in the northern hemisphere, clockwise in the southern. The principle was discovered by a Frenchman named CORIOLIS. He discovered that when a freely moving body moves in an apparently straight line over a rotating surface, and the rotation is then stopped, the path appears to be curved. Our globe, the Earth, has a west to east rotation, with a velocity at the equator of approximately 1,000 miles per hour. But at the higher and higher latitudes, the linear eastward velocity becomes less and less, until it is zero at the poles. Let's imagine we're on the equator, and that we fire a projectile due north. The projectile would have an initial west to east velocity of about 1,000 miles per hour. After a lapse of time, we've moved eastward while the projectile has traveled north. But the sidewise vector of the Earth's rotational velocity imparted to the projectile at the equator is still acting upon it in space, even though the Earth has a lower rotational velocity at this point. From our vantage point on the equator, the projectile appears to have veered to the right. The motivating power behind this apparent effect is known as Coriolis force. Coriolis force is a factor to be taken into account because any non-steered body that moves in the northern hemisphere will be deflected to its right. The Coriolis force always acts at right angles to the direction of travel and is greatest in the higher latitudes, diminishing to zero at the equator. In the southern hemisphere, the Coriolis deflection is to the non-steered body's left. Let's concentrate on the northern hemisphere and see the effect of the Coriolis force on the airflow due to the pressure gradient force. Coriolis force swerves the air, giving us the familiar clockwise winds around a high and counterclockwise around a low. Let's examine this Coriolis effect, taking a minute particle of air as our prospective wind. To have a wind, we first need pressure gradient force, moving the particle from the high to the low pressure area. But the moment the particle moves, Coriolis force moves it to the right. The result is a new line of motion. Instantly, Coriolis switches with it, since Coriolis always acts at right angles to the direction of travel. The pressure gradient force, still accelerating the particle, continues to move it toward lower pressure. The more force applied, and the faster the particle moves, the stronger Coriolis becomes, and the farther the particle moves to its right. After the particle's direction has been turned a full 90 degrees, Coriolis still tries to swing the moving particle farther to the right. But now Coriolis is working directly opposite to the pressure gradient force, and the air can only go where the resultant of the two forces directs it. If the pressure gradient increases, the particle's higher speed induces an increase in Coriolis force. Our particle movement ends up parallel to the contour lines. This air movement is known as geostrophic wind. When you're flying with a tailwind, the low is on your left wing, in the northern hemisphere, that is. But this isn't the whole wind story yet, because the geostrophic wind pattern can be altered. For one thing, whenever anything travels in a curved path, such as around a high or a low, centrifugal force comes into play. In a weak system, with the contours widely spaced and with relatively slight curvature, you can disregard it. But in an intense high or low, centrifugal force plays an important role. It tries to throw the air outward from the center. To see what happens, let's consider a single particle again and geostrophic conditions. With the pressure gradient and Coriolis force in balance, as the particle starts around the curve, centrifugal force tends to drive it across the contour. Momentarily, there's a new line of travel, and Coriolis again acts at right angles to it. At this point, the pressure gradient and Coriolis are both in a direction to retard the wind. As the air slows down, Coriolis and centrifugal force are both reduced to the level at which the two forces achieve a balance with the pressure gradient. The resultant airflow is along the contours, but with a reduction of wind speed. We call this gradient wind. Because of centrifugal force, the gradient wind around the low is lighter than the same geostrophic wind with the same contour separation. While intense highs are less common than deep lows, around a high, the pressure gradient and centrifugal force act together, so the gradient wind is stronger. Another factor that sometimes upsets the geostrophic pattern is friction, caused by obstructions on the Earth's surface. Above smooth terrain and bodies of water, the friction level extends only a few hundred feet. But over high mountains, friction may disturb the winds as much as a mile above the peaks. There is mechanical lifting of air resulting in vertical currents. This vertical motion, both up and down, affects surface winds and in-flight turbulence. Friction reduces wind speed, and Coriolis becomes less. But pressure gradient is not affected, so there is a new wind vector. The wind now blows across the contours. Over mountains, friction may shift the winds as much as 70 degrees, and wind speed may drop 30% or more. The important thing to remember is that friction causes the wind to blow across the contours in the direction of the pressure gradient. This means that with lows, the flow is across the contours toward the center, and with highs, across the contours away from the center. Let's look at our global wind pattern now. From Coriolis force, our high-level flow of air from the equator is turned to westerlies at about 30 degrees latitude. Meanwhile, the low-level flow of air from the pole is turned to easterlies at about 60 degrees latitude. From the overlapping and mixing of the polar and tropical air, the mid-latitudes spawn migrating storms. They generally move from west to east, from the high-level westerlies and Coriolis force. To sum it up, the flow of air around the Earth is in a continuous state of motion, giving us typical wind patterns. The driving force of heating from the sun causes convection and subsidence. High and low pressures result in air movement and what we know as wind. The flow is clockwise in high-pressure systems and counterclockwise around lows in the northern hemisphere. The spacing of the contours is the clue to the speed of the winds. Where they are close together, count on strong winds. As you penetrate the friction level, sometimes found at considerable heights above rough terrain, you'll find the wind lighter, and its direction will be across the contours. But most of the time, when at altitude, you'll be flying under essentially geostrophic conditions. In short, instead of the ancient names for the four winds, become familiar with the four basic elements of wind: pressure gradient force, Coriolis force, centrifugal force, and friction force. And as they say, may the wind be always at your back, then the low will be on your left, right? Right.